In the previous videos, we've been exploring substitution ciphers, where for each character in the plain text, we will use an algorithm to figure out what letter it is substituted by. And so we can go in the forward direction, the encryption, and then following the algorithm in reverse, we will be able to decrypt the substituted letter back to its original. Now, there's another class of there's another class of encryption, of cryptography, and that is called transposition. So rather than substituting one character for another character, what happens in a transposition cipher is that we will instead jumble up the characters in the message, scramble it up such that the original message will not be readable. And of course, just like substitution, there are different types of algorithms. One of the simplest one is the rail-fence cipher. So how does it work? Now, for the rail-fence cipher, you have a secret number, and that determines how many rails you use in your cipher. So from the Wikipedia page, you can see if our secret is 3, we'll set up 3 rails. We will have our plain text, in this case, we are discovered, flee at once. And we're going to write out our plain text on these 3 rails in a zigzag manner. As you can see, down and up and down and up and down and up and down and up. Then we will pull out the letters one rail at a time. So starting with the top rail, we'll pull out the letters WECRLTE, as you can see here. And then we'll go to the second rail and we'll pull out the letters on the second rail, and that will be ELDSOEEFEAOC, as you can see here. And then we'll pull out the third rail, the letters from the third rail, and they will be AIVDEN, as you can see here. Now, this is a ciphertext from the message, we are discovered, flee at once. Looking at the ciphertext, you can see that if the message is long enough, right, it's very difficult to figure out what the original message is. It's a sort of a very difficult anagram puzzle. So if our key is 4, for instance, then we'll set up 4 rails. If our key is 5, we'll set up 5 rails, and so on. In this video, we're going to look at how we will implement the encryption according to the rail-fence cipher in Python code. So we're going to set things up here. We are going to follow the example in the Wikipedia page. So we're going to say our key is going to be 3, and our plain text is going to be we are discovered, flee at once. Okay, and hopefully if our algorithm implementation is correct, we will then get this ciphertext out. So we start off first with our ciphertext being the empty string. So normally in a substitution cipher, we will go through every single character in the plain text and calculate what is the substituted letter. We don't do that in a transposition cipher. And I guess the algorithm for how we will iterate through the plain text will differ for different algorithms. But for the rail-fence cipher, we can kind of break it down into the number of the secret key, right? So in this case, the key is 3. We can break down our algorithm into 3 iterations. So we're going to iterate through the number in the key, okay, right? In fact, let's call it row. And I'm just going to print this out to get 0, 1, 2. So there are 3 rows when the key is 3 and it is 0 index. What do we do next? How do we know what letters will appear in the first row? Well, for the first row, we know that there is a kind of cadence to the letters reappearing. So if we start off with the first letter W, we know it's going to go down and up, and that's going to take 3 letters. And so the 4th letter will reappear on the top rail. Again, we'll go down and up, that will take 3 letters, and we'll find out that the 4th letter subsequently will appear on the top rail. So we want to be able to calculate what is this cycle for an arbitrary key number. So we're going to look at several examples. When key is 3, this cycle is 4. When key is 4, this cycle is 1, 2, 3, 4, 5, 6. And when key is 5, this cycle is 8. So we tabulate it out. We are trying to find a pattern between the cycle and the key. How do we derive the cycle from the key? And by looking at the pattern and adding another column, which is 2 times the key, we know we can see that there is a relationship here, right? 4 is 2 more than 2, 6 is 2 more than 4, 8 is 2 more than 6, 10 is 2 more than 8, and so on and so forth. So we know that the relationship here between the key and the cycle is that the cycle will be equal to the key number times 2 minus 2. Right? So let's now put that in code. We know that the cycle will be key times 2 minus 2. Okay? And we'll be able to pull out from here the top row. Right? So let's start off with, let's say, an index into our plain text. And we start off our index is 0, and we'll have a while loop while our index is less than the length of the plain text. Okay, we are going to build our ciphertext by saying that so this is only for the first row, top row, right? Our ciphertext will be the plain text index into the index, and then our index is gonna increase by the cycle. So let's print out our ciphertext. It's not gonna be all the way correct, but we hope that at least the first few letters, which is the first rail, will be correct. And so we can see the first few letters is WECRLTE, and that is what we are looking for, WECRLTE. So we've gotten the first rail out. Okay, and I'm just going to remove this print statement. We don't need it anymore. Now let's take a look at the second row. In this case, we see that there is a cadence of 2, right? But it is not always the case that we are going to get a cadence that is simple. Let's take a look at when our key is 4. When our key is 4, we look at the cadence on the second rail is going to be 1, 2, 3, 4. 4, and then there's a 2, and then there's a 4, and then there's a 2, and then there's a 4. So the cadence is going to be 2, 4, 2, 4, 2, 4, 2, 4. If we look at the third rail, the cadence now becomes, again, 2, 4, 2, 4, 2, 4. So this is exactly 4, 2, 4, 2, and this is 2, 4, 2, 4. Okay? If we take a look when the key is 5, the cadence, the cycle on the second row is going to be 6, 2, 6, 2, 6, 2. The cadence on the third row is going to be 4, 4, 4, 4, 4. The cadence on the fourth row is going to be 2, 6, 2, 6, 2, 6. So it's a little bit difficult on the subsequent rows after the first rail for there to be a single cycle number, right? There's actually 2 cycle numbers. It seems 1 or 2 cycle numbers. It varies. Okay. So rather than doing that, I'm going to look at a different pattern. Okay. So if you take a look here, you can see that on the second row, right, there are 2 letters that will appear, and the first letter is offset from the top letter by 1 to the right, and then the second letter that appears will be 1 to the left of the next top row letter. And then over here on the third row, the first letter that appears will be offset by 2 from the left, and the second letter that appears will be 2 from the right. Okay, and we see that that is the case for all intermediate rows except for the last row. The problem with the last row is that the offset from the left and the offset from the right is going to collide together into a single character. But we see this possibility here that for the intermediate rows, for the second, third, fourth, until the penultimate row, that we can grab the two characters out from every cycle by calculating the left character from the left offset and the right character from the right offset. So you can see here, there will be offset by, in fact, you can take a look here for this, look at this V shape. For the second row, offset of 1, and then after that is offset of 2, offset of 2. Okay, let's take a look here, and then after that it will be offset of 3, offset of 3 from the left and from the right. Okay, so we're going to use that for the second, third, fourth, all the way until the penultimate row. But for the last row, it's actually going to be the same as the first row, but it's going to be shifted. It's going to be shifted by the number of rows. Okay, so let's implement that first for the last row, right? For the last row, we'll go like, while index is less than length of plain text. Okay, we'll need to offset the index off by a certain amount first. We'll need to offset it by the row number. Index by, will offset by row, right? And then the middle will be the same. Okay, and we'll need to put this behind a conditional to make sure that this code runs for the first row and the last row only. So this one we only run if it's the first row, and for this one we'll only run if it's the last row. Okay, so let's run this, and we'll notice that the first row is still there, and the last row will appear as AIVDEN, which is what we are looking for, AIVDEN. Okay, so we figured out the first row and the last row. Now we need to figure out the rows in between. Okay, so I'm gonna do a else if or elif, and so this will be for the intermediate rows. Right? So how can we do it for the intermediate rows? So we know that there will be actually two indexes. There will be a left index and there will be a right index, right? There will be two characters. Towards the end of the message, there might be one character, but normally there will be two characters. So we're gonna calculate a left index, and the left index will start off with, as you can see here, the left index always starts off, number of row offset from the beginning. Okay, and the right index will be equal to, it will be equal to the next cycle minus the row, right? And so, and the while loop is going to look a little bit harder too, also. It's going to say while the left index is less than the length of plain of text, right? So we're going to keep doing this until the left index goes off the message. But just because the left index is within the message does not mean that the right index is within the message. Okay, so we've got to be careful about that. But nonetheless, we can insert our left index, our left character. Okay, and then we'll do a check before we add the right character. Right, and we'll see that for the both of them actually, we can actually increase it by the cycle amount, right? 1, 2, 3, 4, 5, 6, 7, 8. Right, so we can increase the left index by left index will increase by the cycle, and similarly the right index will increase by the cycle. Okay, right? So it's as if we split this into two rows with one character per row, right? So let me just explain it in color. For instance, perhaps I could say that if I color this and I color this and I color this and I will color this a different color. Okay, so you can see that the cycle of the green letters is 8, which is the cycle we are looking for, and the cycle of the orange letters is also 8. Right, so that's why we can do something like this. Okay, let's see whether we got it right. So we got something out, there was no error, and let's double check against what we have here. And it looks correct. Okay, so let's do a check where we change the key and the message is this is top secret. So let's change the message and there's spaces here. So let's change the key to 4 and see whether it breaks our algorithm, our code. Okay, so this is what it gets. Is it correct? It should be TSS HI space space ET. TSS HI space space ET. I space TP. I space TP. CESOL. That's right. Okay, so now let's change the key to be 5 and let's see whether it works. If key is 5, I should get TTEH space. Or Otis PCSI. Space E space S. So it looks that like we have implemented it correctly the encryption for the Rilfan cipher. So give it a go, see if you can come out with a similar code with your own implementation.